Hello, everyone. This is Dr. White here with the first in a projected two-part series of screencasts for sections 1.3 and 1.4 in our textbook. For the exact parts of 1.3 and 4 that you need to read, please consult Canvas because we're not covering every single topic in those two sections. The slides for sections 1.3 and 4 are combined into one slide set. Let's go ahead and pick up those slides now. So here you are in RStudio. You'll go to the ... /com. Dr. White stuff. Mat 111. Slides. OS 1.3 and 4 slides.html. View in web browser. And there they are. So, we're mostly talking in these sections about observational studies and experiments and the differences between those two kinds of studies. You'll be needing a package TigerStats for these two sections. So you'll want to make sure you've libraried it if you've had to restart your R session for any reason. So we want to discuss the two major types of studies that you learned about in elementary statistics. By studies, I mean, the research into a situation that involves data, where you have some research question that you want to answer. First of all, we want to talk about observational studies. In an observational study, researchers just record the values of all the variables that they're interested in measuring on their subjects. They'll record the values of the explanatory variable for every person in the study. And they'll record the values of the response variable for every person in the study. And then they'll start to look for relationships between those variables. So for example, think about that youth risk 03 data that we looked at previously. The researchers recorded a lot of variables. We were interested in two of them. But the point is, they just recorded them on the students. They asked the students, how often do you use sunscreen? And gave them these possible answers and recorded those answers. And they asked the students, what grades do you typically make? And gave them some possibilities to pick from and recorded their answers. They didn't do anything to intervene in what the value of a variable might be for a student. They just recorded the variables as they saw them. Next, an experiment is different. In an experiment, the researchers assign the values of the explanatory variable to the subjects, and then they just record the response variable. For example, the stints study that we've talked about was an experiment because the researchers randomly assigned subjects to receive a stint or not. So when you think about that group variable that was in the data that said whether the subject was the treatment or control, that wasn't something that that each subject just had about themselves, and the researchers just recorded whether they were in treatment or control. The researchers actually decided whether a subject would be in treatment or control. They used chance to do that, but they reached in and they made that happen. And that's what makes this an experiment, not an observational study. Now, there was a response variable in the study. It was the outcome variable, and the researchers did just record that. They didn't make anyone have a stroke or anything like that. They just waited a year to see whether each person would have a stroke and recorded what happened. Experiments have certain advantages over observational studies. They can be very helpful when you want to answer causation questions. Does one variable cause another? Observational studies are often used to investigate causation as well, But the problem is they're subject to confounding factors. And you're going to ask, what do I mean by causation? And what do I mean by confounding factors? So before I get into why experiments are so useful for studying causation and why they avoid confounding factors, let's learn more about those concepts. First of all, causation. That's one of the most common reasons that you want to study the relationship between two variables. It's to see if one of them causes the other. Causes. What do I mean by causes? Let me pick up an example here to help us think about it. We tend to think that speeding causes tickets. Pictorially, we could imagine this little circle here as representing a variable, speed, which can of course differ from one person driving a car to another. I drive 55, you drive 85 down the same highway, and another person drives 20 miles an hour. Speed can vary. It's a variable. And ticket, maybe that's a variable with possible values yes and no, and that's whether or not the person gets a ticket during this drive. And this arrow that runs from speed to ticket, that symbolizes causation. So this is just a graphical way of saying that speeding causes tickets. Well, that's the notation, the graph way of saying speed causes tickets. But we need to dig deeper in order to think about the concept of causation. One thing you want to realize right away when you say that one thing causes another is you don't necessarily mean that it's the only thing that's involved in causing the other thing. Like speed, the speed that you drive a car is not the only thing involved in whether or not you're going to get a ticket. Like if you just drove down an empty highway, then you certainly wouldn't get a ticket because there would be no cop there to see you. So another variable, you could call it cop sees, two values, yes and no. That's also involved in causing whether you get a ticket. And there's probably other variables too that are involved in causing whether you get a ticket, like cop catches you, yes, no. You persuade cop not to give you ticket, yes, no. All kinds of other variables. So what I'm just saying here is a thing can cause another, but not be the only cause. It can be a partial cause. That's part of the idea of causation. You should also keep in mind that when we say one thing causes another, it doesn't have to be the direct cause. So like we say that speed causes tickets, but the pressure you put on the accelerator for your car causes your speed. And so there's a chain. Since accelerator pressure causes speed and speed causes ticket, then accelerator pressure causes ticket. So accelerator pressure is still a causal factor in getting a ticket, even though it's not the most direct cause of getting a ticket. So the rough idea of causation is this. We say that speed causes tickets because we believe that if two people are alike in every way, except that one drives faster than the other, then the one who drives faster has a bigger chance of getting a ticket. This rough idea of causation is the one that we'll use in this course because it takes into account that causes can be indirect and partial. Here's another cause question. Does smoking cause lung cancer? One trick you're going to have to learn in statistics is to be able to go from the cause question in your mind to thinking about the variables that would be involved in studying that question. I see two variables here. I guess you could call it one of them smoke, and its possible values are yes and no. So like each individual could either be a yes smoker or a no not smoker. And that variable that you can measure on a person I'm going to think of it as the explanatory variable, because I think of it as something that might be able to cause this other variable, lung cancer, yes or no. Every person can have lung cancer, yes or no. So typically, cause questions can be broken down like this. There'll be at least one explanatory variable, and there'll be a response variable that you think is maybe caused by the explanatory variables. So thinking back to our rough definition of causation, then the question, does smoking cause lung cancer, is really this question here. If two people are alike in every way, except that one of them smokes and the other does not, is the one who smokes more likely to get lung cancer? Now, I want to make an important distinction that we've actually alluded to earlier on in the course, that there's a difference between association, relationship, dependence between two variables that we've looked at a little bit before. There's a difference between that and causation. To help us talk about these two ideas at the same time, let me introduce some more notation. I'm using the solid arrow to represent causation. Speeding can cause getting a ticket. So the variable speed causes variable ticket. But I'm going to use this dotted line that doesn't have an arrow one way or another to represent that two variables are associated. Speed and ticket are associated. And you know what? Whenever there's causation, there's going to have to be association. Causation implies association. Whenever one variable causes another, the two variables are going to have to be associated. Think about why this is so. Speeding causes tickets. The more you speed, the bigger is the chance that you'll get a ticket. And so what happens is that if you look at a lot of people, you'll find that the ones that have higher car speeds tend to have tickets more often, and the ones with lower car speeds have tickets less often. So the values of the variables go together. That's association. Causation implies association, but not the other way around. Two variables can be associated, but neither one has to cause the other. Let me give you an example. It's based on just fake data that I made up, but play along with me here. Imagine this scatter plot here, where every dot is a town, and the x-coordinate of the dot is the number of dogs in the town. So like this town here looks like it has about, 12,500 dogs maybe in it. And the y-coordinate of the dot is how many fire hydrants are in the town. So this town here has a little less than 1,100 fire hydrants. Now look at all the towns together. The cloud of points is a rising cloud. It rises as you go to the right. And so towns with a large number of dogs tend to have a larger number of hydrants, fire hydrants in them. And towns with a smaller number of dogs have a smaller number of fire hydrants. So clearly, we've got a positive association here, as we've learned how to say in previous chapters. The two variables, number of dogs and number of fire hydrants in a town, are related, they're associated, but neither one of them causes the other. I mean, think about it. Could the number of dogs cause the number of fire hydrants? How would that work? Like, the more dogs there are in town, I don't know, the more they go badger people in the city council to put fire hydrants in? I don't think so. Or the other way around, could the number of fire hydrants cause the number of dogs? Like if a town installs more fire hydrants, then maybe dogs all over the state hear about it and wander over to that town so they can pee on the fire hydrants. It just doesn't make sense. These two variables, neither one of them causes the other. So clearly there's an association. We saw it in the scatter plot, rising cloud points. But the reason there was an association was not that one variable caused the other. Actually, the reason in this case would be that there's what we call a common cause, a third variable that's causing both the explanatory variable, number of dogs on the x-axis, and the response variable, the number of hydrants on the y-axis. Think about it. The more people there are in town, the more dogs there are going to be because people take dogs as pets. But also, the more people there are in the town, the more houses there are going to be, and therefore the more fire hydrants have to be set up to take care of those houses in case of fire. Common cause. That's how to explain the association this time. That's enough for this screencast right now. Having made the distinction between causation and association, I want to show you next time about a feature that can come up in observational studies that makes it very difficult to infer causation, even when you can clearly see that there's an association in your data. See you next time.